All right. So we've made the rounds. So we're very happy today to have Brian McNamara to tell us about the work he's been doing recently. Brian was an undergrad at Villanova, I think, and then got his PhD at Virginia. And then you went to Groningen, right, for a postdoc?
Mm-hmm.
Right, good. And then you were at Ohio University for
6 years.
6 years, okay. And then was at CITA and has been at Waterloo now for almost 10 years.
8 years.
8 years, yeah. Good.
So it's time to move again.
Okay, so tell us about gas flows and galaxy clusters. See, I have to say, you convinced me of something I didn't think was true, but it is.
That still doesn't mean it's true, but I'm more confident now. Well, thanks everybody for having me. It's always a pleasure to be back in Toronto. I've already been taken to task about the original smelling of this. So gas flows, this is the verb and not the noun, in galaxy clusters, which is part of a larger topic, which is known as feedback. And it's a relatively new, in the last, I don't know, 10 or 15 years, a new view of how galaxies have formed and evolved. So the first more than half to two-thirds of my talk will be background on this, and then I'll show some new observations that we've received from Chandra and from Alma. So I'll give this background about feedback, talk about two types, but I'm going to focus on this other mode called radio mode, which is energy that's deposited in a cycle, a cooling and heating cycle in modern-day galaxies, well, for about half of the universe, by, as the name implies, radio galaxies. Although most of the energy is, of course, not in the radio. It's coming out in mechanical form, and I'll show you the evidence for that. And also that these things are driving very massive outflows. And even what you might think of as relatively nascent galaxies today, there's as much gas going out as there is going in, which is pretty interesting. And then some new results that I did with a student last year, Robert Main, who's now a student here, which is the connection to of feedback, the energy pumped out from black holes by the energy pumped out by radio sources proportional to the mass of the halo, which has interesting consequences. So I want to point out my team members. Helen Russell is an ex-postdoc, Robert Main, an ex-student. I'll have 2 slides from his thesis and a number of others that I've been working with for a while, Adrian Vantium, who's a student. And of course, this guy here, I have a question mark because when I went to go find your picture, I typed Norm Murray, and I looked online. I said, whoa, you have a hobby. So apparently, there's a photographer named Norm. Well, I won't go into that. Anyway. It was a racy hobby. So anyway, Norm has been involved, and it's been a real blast working with Norm on some of the ALMA stuff, because I've learned a lot from working with him, and I think we're coming up with some interesting stuff. So I mean, to sort of pitch this in the broadest sense, the question that we've been looking at for a long time comes down to, why are these galaxies red and dead? And when I was a lad, the answer came primarily from Egan, Linden, Bell, and Sandage, which is it's some combination of angular momentum and cooling time. Things that formed in halos or galaxies with large angular momentum ended up forming disks. It settled in, and star formation occurred very slowly, whereas systems like the giant elliptical galaxies formed very rapidly and had very little angular momentum. And they burned up their fuel very quickly, and it was extinguished, and they've been dead, for the last 10 billion years or so. But what they didn't know about then were dark matter halos, which is, of course, what dominates the mass, but also the whole lambda CDM cosmogony, which says that little things form first, little dense things, and then they grow into bigger things. And the standard prediction today would be that the biggest things should be forming stars very rapidly, and of course they're not. So they didn't know about that, but the other thing that they didn't realize is that these things weren't gas pores. So astronomy was dominated at that time by, this is sort of a cheesy attempt to use Photoshop here, so you'll have to forgive me. But this is an image, instead of in the optical, it's obtained in the X-ray and the radio, and what you can see in the X-ray is this blue stuff here. I'll show you some better pictures in a minute. That's the hot halo in the gas. That's the gas at the virial temperature. That's at a temperature between 10 to the 7 and 10 to the 8 degrees. And of course, in red here is the radio jet that's emerging from the central black hole, and as I'll argue, is heating up this halo and keeping it hot. So the notion that these galaxies formed and all of their fuel was burnt very early on, and so they've just been dormant ever since, is incorrect. The fact is that they're sitting on storehouses, repositories of gas, but that gas is hot. And in principle, the gas should cool and form stars, and in general, it doesn't, or at least it does so very slowly. And the reason is because of this black hole at the center, which is continually, it turns out, pumping out energy. So these galaxies, which are known as being red and dead, are hardly dead. They tend to be red, but they're not dead, and what's keeping them going is the black hole at the center. So in this concept of feedback, and I have a specific notion of feedback that will permeate the talk, and that is not just energy being pumped out of a black hole. As you know, if you drop matter onto a black hole, the binding energy, the gravitational binding energy, will be released in some form or another, whether it's radiation or mechanical power. That energy will be imparted onto the surrounding medium, depending on the form of the energy. And in the case of giant elliptical galaxies, it comes out primarily in the form of mechanical energy. It keeps these halos hot, although some cooling does occur, and I'll show you the evidence for that. It fuels the black hole. It fuels some measure of star formation, and this cycle can repeat in a way that may have given rise to some very interesting relations. And in the current parlance, you may have heard of two types of feedback. One is known as the quasar mode feedback. Okay, and this operated early in the universe. It's essentially quasars, which drove fast winds and radiation outflows of neutral and atomic gas. And the idea is that in the early moments of the galaxies, they were able to, driven primarily by this thing known as the M-sigma relation, which I'll show you in a minute, which is this remarkable relationship that was discovered late in the last century, I guess I can say, known as the M-sigma relation between the mass of the central black hole and the mass of the galaxy, or its velocity dispersion. And it turned out to be this remarkable relationship where the slope between the mass of the central black hole, measured in a way that I won't get into here, and the mass of the galaxy scale in this constant ratio, regardless of the mass of the halo, at a ratio of 700 to 1. And it implies that for every 700 atoms or so that went into forming stars, one atom fell into the black hole, and this grew over many decades in mass. And the idea is that these fast outflows and winds imprinted, or likely imprinted, this relationship. The form of the relationship scales somewhere between sigma to the fourth and sigma to the fifth, where sigma is the velocity dispersion of the galaxy. And whether this is an energy balance or momentum balance isn't clear, but it's been worked on by many people, notably a very influential paper by Norm in 2005. And so the idea, or what many people believe, is that this is the primary mode that gave rise to the black hole and the galaxy that we see today. But as I mentioned, these galaxies today are not devoid of gas. Much of the gas was driven out, but they're also filled with a hot halo, which comprises a lot of mass. And that hot halo then should serve to fuel star formation through the ages of the galaxies, and generally it doesn't. And we think that that's due to this thing called the radio or mechanical mode, which occurs at late times, and it operates primarily on the hot phase, or so we think. And this is what keeps galaxies red and dead. And I'll describe that in more detail. And the consequences for galaxy formation today can be sort of boiled down into these two figures, I suppose. One is the luminosity function of the galaxies here. So this is the number of galaxies per unit luminosity, per unit volume in space today, versus the total light emerging from the galaxy, or its absolute magnitude. And what you can see is that this turns over. It's got a certain shape here, as shown here. And the interesting thing about this shape, I won't go into all the details, but it's very hard to predict this just from pure lambda CDM. There's pure gravity and pure cooling. What you would actually predict is a form that looks something like this blue line. You expect today galaxies to be much brighter, much bigger, and much bluer than what we observe, but instead they don't. They drop off. The numbers of bright galaxies drop off dramatically, and their magnitudes drop off as well. So in other words, they should be bigger and bluer than we see them today. And what this shows is the result of a simulation where energy added from feedback from supermassive black holes is able to suppress galaxy formation at high ends. And the idea is there's enough energy in the black holes to do that in the high mass regime, and then in the low mass regime, feedback kicks in and prevents galaxies from growing to larger sizes due to winds from star formation. So the idea is that low mass galaxies are controlled. Their destinies or sizes are controlled by stellar winds, and massive galaxies are controlled by supermassive black holes. And the idea is that this has given rise to this relationship known as the M-sigma relationship, which I just described, which is the mass of the bulge versus the mass of the black hole. And you see this marvelous trend here, which has a 700-to-1 ratio. So that's more or less where we're going in a nutshell. And now what I want to do is describe the best evidence for this little piece of the puzzle. I won't talk about winds from star formation. I'll talk about the most massive galaxies and the evidence that black holes are able to suppress the growth of massive galaxies. And I think that one of the earliest problems which exemplified this, or issues, or let's say problems related to the bigger problem, is this thing called cooling flows, which they were once called in the 90s. And what I'm showing here on the left-hand side is an X-ray image of the Perseus cluster. And what you can see here is X-ray emission from a very hot diffuse gas. So the temperature, the mean temperature is about 5 times 10 to the 7 to about 10 to the 8th degrees Kelvin. And it's emitting very strongly in the central region. And if you take this and show it on a 3-dimensional plot where you just see surface brightness versus space here, you can see that the emission, the X-ray emission peaks very strongly on the center of the galaxy. So if I were to take this slice here and show where that would land on this picture, it would be something like that. And if we were to take a picture in the visual, which is what's shown here, you see a giant galaxy sitting right at the center of the X-ray emission, and in red is H-alpha emission. So you see gas or emission from gas cooling out at about temperature of 100 million degrees or so, 10 to the 4 degrees, cooling out and accreting down onto the galaxy. And in addition to this, what you can also see here are these holes or bubbles, which I'll talk about in a minute. But the X-ray luminosity is extremely bright in the center of the cluster. And if you just take the gas density and divide by the cooling time, you get an accretion rate that's about 1,000 solar masses per year. So the galaxy should be forming stars at 1,000 solar masses per year. And all ellipticals share this property, some to a greater or lesser extent. But the gas should be cooling down and forming stars in all ellipticals. And it is, but it's doing so only at about 20 solar masses per year. So it's dramatically reduced by many orders of magnitude. And this was a problem for a very long time. Why isn't the gas cooling out? And it turns out that the answer to this is related to why galaxies haven't grown to much bigger sizes. All galaxies haven't grown, and that is the AGN at the center, which you can see by these bubbles, is pumping enough energy in to offset that cooling. And I'll show you the evidence for that in a few minutes. And it turns out that these bubbles, this is Perseus again. You can see that in the X-ray emission there are these big holes. There are two giant holes in Hydra A. This guy's known as MS0735, and I'll show you in a second. There are two giant bubbles or holes in the X-ray emission. When you put the radio emission and optical emission on top, this is what you see, something quite different. This is a picture taken with Hubble showing the galaxies, and you can see these holes are now filled with radio emission. And the scale on this is remarkable. So these holes are 200 kiloparsecs across, and they've displaced nearly 1 trillion solar masses of gas. So they have to push the gas aside, indicating very large mechanical powers. And here is Perseus. You can see it's nicely filled with radio emission. This is Hydra A. This is the first one we saw with Chandra in 2000. And you can see these bubbles are nicely filled by radio emission. And you see various scales. In this case, these bubbles are are on the scale of the galaxy at the center. Same thing with Perseus. But in this guy, they're cluster scale. There's an enormous amount of energy being pumped in to the intercluster medium. In fact, it approaches 10 to the 62 ergs on this, which is the binding energy of about a several 10 to the 8 solar mass black hole. And it does that in a period of about 10 to the 8 years. So it's an enormous amount of energy being extracted in a very short period of time. And this is a ubiquitous thing. So here's a Hydra A, just to give you another example. This shows the original image that I showed just a minute ago, showing these holes that are on the scale of the galaxy. And when you go out, further out, you pan out and take a very deep image in the X-rays and do some image manipulation. You can see that there are these enormous cavities that spread out in the inner 500 kiloparsecs of the cluster. Yes?
So in these types of sources, what's the ratio for mass growth rate of the black hole, which you can estimate from the energy coming directly out of the black hole to the cooling rate of gas out of
the amount falling into the black hole is a tiny fraction of the amount that should be cooling.
Wow.
With
1 in 1,000.
Oh, I see. Oh, that's yeah. In other words, do they follow the M sigma relation? The answer is yes, but it's a longer story. But yes, they roughly come in at about 1 in 1,000. So yeah, and to continue, when you look in low frequency, so in high frequency, you tend to see these powerful, at 1.4 gigahertz, you see the inner region, these relatively new jets coming out at the center, but then filling these giant lobes here that go out hundreds of kiloparsecs is you see that much better at lower frequencies. This is about 74 gigahertz, and you can see that at lower frequency, this stuff fills, it fills it up just like a glove. So these are the older electrons that are decaying, but still very powerful. And again, in this system, it's also the total energy is greater than 10 to the 61 ergs, which is an enormous amount of energy.
Is that assuming that the comparable number of protons stay kept?
I'll get to that in just a second. So the way we work that out is in X-rays we can measure the density and the temperature of the gas to a great precision. So if you have the temperature and the density, then you can multiply the two and you get the surrounding pressure. And so that then pressure times the volume gives you the energy, which is shown here. And so we can use this to calculate the enthalpy. Then we then measure the size of it, assume some three-dimensional distribution. This gives us the total energy, where the energy is proportional to PV times gamma, which is just describes the gas filling it. If this is so it's the ratio of specific heats of the gas, and you get 2.5 PV or 4 PV depending on whether you have a relativistic gas or a non-relativistic gas, and that gives you the total energy We assume that these things, we're observing things generally at late time. We see them ubiquitously. They can generally rise we'll see them crossing roughly twice their diameters, so they're stable over at least that period of time. And so they should be dominated by buoyancy. Their kinematics should be dominated by buoyancy. And so just by measuring its position with respect to the nucleus, correcting for orientation effects, that gives us the time scale. And these time scales are generally a few 10 to the 7 to about 10 to the 8th years. So if you just divide the energy divided by the time, that gives us the mean power over that particular outburst. So that gives us the energy. And as a check in several of these, they're also surrounded by shock fronts. So you can see over here this very sharp delineation here right around in the X-ray. That's actually a shock front. We see a small temperature jump across that shock. And that as well gives us an independent measure of the energy. And the shock power and the cavity powers are generally good to a factor of 2. And when you add it all up, and we've looked at now almost 50 systems, they have energies from anywhere from 10 to the 55 to 10 to the 62 ergs. So that gives us the total power output from the black hole. We can then use that, and we can compare that energy output to the amount of cooling, the energy being pumped out in X-rays. And as I'll show you, over a very large range of masses, they're about equal. But one of the interesting things that came out of that gets to Peter's question is just the ratio, just how inefficient they are, how inefficient radio sources are as radiators. And it turns out they're radiatively very inefficient. So this shows the jet cavity power on this axis, which is determined just as I just described, versus radioluminosity. And for a long time, we didn't know what this ratio was, so people might assume 10 to 1. We always knew that these things are radiatively inefficient, that they were dominated by mechanical energy, but we didn't know by how much. And these are dashed lines of radiative efficiency, where it's 1 to 1, okay, 10 to 1. In other words, the mechanical power is 10 times that of the radio power, 100 times, and 1,000 times. And the amazing thing was that these, in general, are anywhere from 100 to 1,000 times more mechanically powerful than their radio emission. So the simple takeaway message is you measure something with a radio telescope, and even a relatively feeble radio source could be extraordinarily powerful mechanically. And in fact, the galaxy, which looks red and dead, has no evidence of quasar activity, and has a moderately powerful radio source, can actually be as powerful as a quasar. It's just that the energy is being pumped out mechanically rather than in radiation. Now, why does it do it? Again, that's a long discussion, but we think that it gets down to the structure of the accretion disk and the rate that matter is accreting onto the black hole. So in the early stages, in the nascent universe, when quasars were forming, they were accreting roughly at the Eddington rate. They ended up with thin disks that radiated primarily in the ultraviolet. And then as time went on, the accretion rates dropped below a few percent of Eddington, and we ended up with disks that were geometrically thick and optically thin, and gave rise to jets. And in this regime, the energy that comes out is primarily mechanical energy. So what happens to that mechanical energy? Well, this is what's keeping galaxies red and dead, or at least regulating star formation in them. So this, again, is jet power calculated just as I've described before, versus the X-ray cooling luminosity, or in other words, the integral under this big spike. This is the energy that has to be replaced in order to prevent the gas from cooling out and forming stars. And this is shown here for 1 PV of work per cavity, 4 PV of work, and 16 PV of work. And for a relativistic fluid, we would expect something like 4 PV of energy. And what this shows, remarkably, is that these are fine-tuned over many orders of, about 8 orders of magnitude in cavity power, 6 orders of magnitude in cavity power, and a similar range in cooling. And so you can see that you know, for this 50 or so sources, they all line up around this line. But the other thing that's very interesting here is somehow these systems seem to know when they need extra power to offset cooling, the black hole gets that information. So the fact that we're seeing this envelope or trend tells you that these things have to be sitting or likely are sitting in this regulated feedback loop. So as gas begins to cool very strongly, say on the high end, that information gets down to the black hole, presumably by accretion, and power output increases proportionately. So they know about each other. So that's, you know, that's a result that's been around for a while. But one of the other things that I've started looking at with students, one of whom, Robert Main, is now a PhD student here, is how does this scale with mass? So, and I was expecting that we would find some correlation, but I was a little bit surprised at this. You know, as you know, the black hole mass through the m sigma relation scales with the mass of the halo. But the question is, does the power output know not just about the cooling, but about the mass of the halo? And in fact, it does. This shows, again, power output, as I just described, versus M2500, which is the mass of the halo. And you can see that there's a very nice correlation between power output today and halo mass. So one question that comes up, is it halo mass or is it galaxy mass? And you might expect, you know, halo mass is dark matter. Black holes don't live off of dark matter. They live off of baryons. And so you might expect that it's related to, you know, the mass of the galaxy. So this is the gas mass. This is the halo mass in hot gas shown here. And we also see a similar trend, but with a bit larger scatter. And we've also done this for galaxy mass, and you also see a trend between these masses. So we don't know, you know, what the primary parameter is, whether it's total mass, whether it's gas mass, whether it's galaxy mass. But the interesting thing is it does scale, and it scales in a way that making very simple assumptions is consistent with the m sigma relation. Now there's an additional piece of the puzzle which I'm just going to mention. I don't have time to show. But this trend vanishes when you play this game for systems with cooling times, central cooling times. That, in other words, systems that don't have this central X-ray spike. So they have long cooling times. And no, I don't think so. I'm glad they were thinking of me there at Adobe. So for systems with long cooling times, this goes away. So it seems that this boils down in a simple way to two simple, relatively simple parameters. One is how fast the gas is cooling at the centers of the halos, and the halo mass. And when you give it those two parameters, you can, with this relationship, predict how much power on average is emerging from the central black hole. We're still trying to, you know, chew through this, but it seems to be, you know, quite a remarkable thing, and it's also a convenient result for modelers, because now people have made generally very simple assumptions, sometimes unrealistic assumptions, about how accretion works on the central black holes, and use that to try to model feedback. And in this case, you know, for people who are doing n-body models or MHD models, you can now take these scaling relations and just stick them into your model and then evolve them simply based on halo mass, which is a number that's very well determined in models. And finally, on this topic, before moving on, I wanted to point out that the heating agent, this heating is remarkably efficient. And so what's shown here is the mass, the stellar mass of the central galaxy in these clusters, divided by M2500. So the stellar mass divided by the total mass of the halo. And this reproduces a very well-known result, which is that galaxy formation gets less and less efficient as you go to higher mass. In other words, you know, as this is versus M2500. So in other words, the halo, the galaxy grows much, much more slowly relative to the halo as you go to higher mass systems. And what's shown here are galaxies that have very long central cooling times. That is, the cooling time in the center of their halo exceeds a gigayear. So cooling is very inefficient in those halos. And galaxies that have cooling times less than 1 gigayear. So they should be cooling prodigiously if feedback were not operating. And what this line shows schematically is where these black lines should be if cooling continued in an unimpeded fashion. And as you'd expect, galaxies should be much bigger, much brighter, and much bluer, and they're not. And in fact, the two populations, the long cooling time and the short cooling time populations, lie right on top of each other. And that tells us that feedback is operating very efficiently and has been operating very efficiently throughout most of the age of the universe. So they're they're critically tied. The black hole seems to know what's going on in these systems on very large scales.
What do you know about the duty cycle of this feedback? You say it's
So
continuous, but is it?
So the typical central cooling time in these systems is 5 times 10 to the 8th years. I'll say less than a gig a year. And we have systems where we have multiple cavity systems. These bubbles, we see it through multiple duty cycle. And the answer is it's less than the central cooling time. So it's the cooling time that's triggering the duty cycle, which is what you need to have efficient feedback. So somewhere between 5, 10 to the 7, and 10 to the 8th years, depending on the mass of the halo.
The other way to phrase it is for everything that has a short cooling time, like 80% or 90% of them are radio sources.
That's right.
That's a similar number has star formation above a few solar masses per year.
That's correct. Yeah. So as soon as you pick out the short cooling time systems, you find that they're on. And when you pull out the long cooling time systems, they tend not to be.
What's the redshift rate?
This goes out to something like 0.2 and then becomes, it's relatively nearby. I made a general statement because we've looked out as far as 0.6 and we don't see any diminishing of this. So we've explored out to almost a redshift of 1. Okay, so the next topic that I want to cover here is outflow. As I just described, the radio sources are very efficient at heating the gas, but they also drive it out. And it turns out that, just looking at normal clusters, the galaxies in relatively normal clusters, you wouldn't realize or you wouldn't know without looking in detail that there's as much gas flying out of these systems as there is cooling down into the center. So it's not just heating that's regulating these. It seems that these things are actively throwing gas out into the intracluster medium and into the interstellar medium. And in doing so, they're also ejecting metals. And in fact, we use metals as a tracer for this. So what am I showing here? This is the image that I showed a little while ago, where in blue you see the X-ray emission, and in red you see the radio emission. And as I mentioned, with X-ray telescopes, we can measure the temperature and density very well in these systems. But the third parameter that we measure very well is the metallicity of the gas, the metal content. And this is not pristine gas. Okay, it's in general the gas in the spread throughout the intracluster medium has a metal enhancement, or it's enriched to about 1/3 of the solar atmosphere. And in cosmic terms, that's metal enriched. And where do the metals come from? They come from the stars. The metals are created in stars. And you have the biggest galaxies in the universe, with presumably the biggest black holes sitting right down at the center of these galaxy clusters, and they're churning out metals. And as you go into the center of the galaxy cluster, so this is the straight image on this side, and on this side you see a metal image. And I've just adjusted the contrast so that anything in red or yellow means it's approaching 1 solar metallicity, and anything that's in blue, it's about 1/3 of the solar metallicity. So you can see out here, this is about 1/3 of solar. That's the average. As you go to the center of the galaxy, which is churning out these metals, the gas metallicity, the gas phase metallicity rises to about solar metallicity or so. And what we found, interestingly, is that this gas, which was presumably just created down in the center, is stretched out into these things, I like to call iron streaks. And we see these in many systems, where the metals and gas that were created down here, and the iron fractional metal content is only about 1 part in 10 to the 4 here. So most of what's being moved out, as I'll describe, is just regular gas, hydrogen and helium. And you can see that it's being dragged out right along the jet axis. And it's a lot of stuff. So it's displacing 10 to the 10 solar masses or so, or a little bit more. And the outflow in this thing, the implied, we can measure the amount of mass that's associated with these iron streaks. And we know how long it takes to get that stuff out here because we know what the rise time is. And you end up with outflow rates of 100, several tens to more than 100 solar masses per year. And it turns out that these outflow rates are comparable to the rates of star formation when we see star formation in the centers of these. And it's very interesting. It's interesting that these numbers are very similar to what are seen in nascent galaxies in cold gas that's being thrown out at a redshift of 2. So even in this thing, if you were to take just the visual image of this thing, you would see just a normal red and dead galaxy. And it turns out gas is flying out of this thing at well over 100 solar masses per year, and taking the metals along with it, so that the metals that were made in the center now are getting dragged out into the intercluster medium, and this may be how much of the metals that are distributed throughout the intercluster medium get there. They get dragged out by the radio jets. This was an interesting result. We found this in a couple, and a former thesis student of mine looked at this in general and found that there's a very nice relationship between the extent of these metal flows and jet power. So it really ties it in. What we can see here is that for systems that have jet powers approaching 10 to the 46 or energies well over 10 to the 61 ergs, these things it's driving outflows out to at least 300 kiloparsecs. And for objects like M87 or so, this is getting out to many tens of kiloparsecs. So these jets are not just heating, they're driving the gas out, and they do it in a very nice, predictable way. And it's to the point now where we can make metallicity maps and use that to infer how powerful the jets were in the past. And we've also looked into just the overall metal distributions in the centers of clusters. And if you just say, if you just ask how much energy would be required to distribute this stuff throughout the center of the cluster, you work your way back, figure out how much mass would have had to have been dropped onto the black hole to drive that stuff out. It's just gravitational potential energy, and it turns out you get numbers that agree with what we expect the central black hole masses to be.
Do you see any trends between the ratio of the metal enrichment radius to the burial radius?
We haven't looked at that.
Mass.
Yeah, we haven't looked at that yet. But that's a good question. That's something.
You expect that because the black holes are proportionally more massive.
You would, and if you fold in the other relationship to this, you should get it. We talked about that, but we haven't actually gone through and worked it out. But that's a very good point. So these are hot outflows. So the temperature of the gas in these outflows is about 10 to the 7 or 10 to the 8 degrees. What about the cold gas? That's the stuff that's doing the action. That's the stuff that's feeding the black hole, and it's also the stuff that's feeding star formation, which is observed in many of these, such as Perseus, which I described before.
Before you go on, can I just ask you
Yep.
a simple question about the 3D metallicity?
Yep.
And the small scale jet doesn't look like it's aligned with the lobes, right? The middle.
Oh, this thing. Yeah.
And so does it precess or something over time? And how did the 0.3 in the blue area get to be 0.3 instead of a lot smaller? If it wasn't being, how does the flow work that somehow gets the high metallicity stuff mixed with the low metallicity?
So I think there are a couple of questions there. How did it get up to 0.3 to begin with? It got up to 0.3 from primarily it was seeded by early star formation. So most of the metals in the halo probably arrived before the cluster formed. And so the gas was already pre-enriched when it fell in from the very early phases of star formation. Okay? And
That's a fossil.
that's a fossil. That's right. And then this stuff was probably created in the last couple of billion years just through normal stellar evolution. And then that's now being pushed out. Now, how did it get spread around? How did the metals get pushed into the rest of the cluster? Remember, every one of the galaxies in the I'm focusing on the central galaxy because it's the one that gives us the most information, but they all have black holes. They're quite large. This should be going on in every galaxy.
So the information is not as detailed in almost all clusters as in this one. In other words,
this is one of the better ones, yeah.
So the question is, you have a few really good concrete examples.
Yep.
And then is the larger set.
Then you go to
sort of
that.
Generalized metallicity that's
Yeah.
known. And one is inferring things, which the question is, how solid a basis is that this tie-in you're doing, which is a great story, but if you were to say how many objects really give you strong evidence for tying everything together so you get this
correlation?
polar relationship.
Yeah. So I think it's pretty good. I mean, some of them are better than others, but this isn't made by looking at a map and pinning a number down. We actually go through and measure it over all angles, azimuthal angles,
For every one of those?
for every one of these, yeah.
Oh, okay.
Yeah.
That was the
We
question.
actually do a serious job. That's just a picture. There are no measurements made off of this picture. Okay, nothing that appears in this diagram came from an image like that.
And you can do that for the ones that are sort of
Yeah.
50 kbc?
Yeah, you can.
Because you got that lower bit, and
Yeah,
it
but
looks
second
like...
one, M87, it's next door.
Yeah, I mean, M87 was one of the first ones we did it, and you see it very clearly in M87. And Hydra A was the one we first saw it, and it was very clear in that one. And then, you can see there is scatter in there, so some of them, and the metal distributions are not simple either. When you dig into the noise, they're complicated, but this is a fairly blind approach, and we don't actually pick the stuff off of pictures. We do serious measurements with it.
So I'm ashamed to say MS0735 is not emblazoned in my consciousness. What is the mass of that cluster?
Oh my God, Dick. I mean,
Yeah, can you believe it?
can you believe it? It's massive. It's about a 10 keV cluster, so it's approaching 10 to the 15.
10 keV cluster, how far away is it?
0.2.
0.2, right. Is it in a big supercluster?
That's a good question. It's in a very massive cluster, but I don't know whether it's in a supercluster.
Okay, so it's a 10 keV cluster.
Yeah, 8 keV, sorry.
8 keV.
Yeah. And it's a good question. I mean, well, I'll tell you later how it was selected, but it was pretty innocuous. This was actually a control object for why this thing didn't form stars, and it turned out to be the most interesting thing in the sample. So, but that's a story for another time. So just in the last few minutes, I want to discuss some really new stuff from ALMA that I've been working on with, among other people, Norm. These things are forming stars. It turns out that in many of these systems, they're extremely gas rich. So Alistair Edge, a colleague of mine, more than 10 years ago, did a survey looking at molecular gas in the cores of clusters to see if, at that time, quaintly, to find the missing gas that should be cooling out and didn't seem to be. And it turned out that these things, in some cases, they approach 10 to the 11 solar masses of molecular gas. Now, to put that into scale, the Milky Way is a burgeoning galaxy, and we have a few 10 to the 9 solar masses molecular gas. So for some of these that have very high cooling rates, their masses exceed 10 to the 10 solar masses of molecular gas. So we decided to focus on those, and we have projects in cycle 0 through 2 with ALMA, which, by the way, is just this marvelous telescope. I won't have time to describe much of it, but we have a program. We get a couple of targets a cycle, which isn't a lot, but we're grateful to get it because it's not easy to get. And we wanted to ask a couple of questions. What's the origin of the molecular gas? Is it fueling star formation in the black hole? But more interestingly, what is this feedback cycle doing to the molecular gas? And my initial bias was nothing. Okay, this gas is 5 orders of magnitude more dense than a typical radio jet. And so it's probably ballistic. It's ending up in these disks. We're going to look down and we're going to see disks with star formation, and the jets aren't even going to know about the molecular gas. And that turned out to be incorrect. We observed about 5 brightest cluster galaxies. And what's shown here are the objects of choice, Abell 1664, Abell 1835, Parkes 0745. These numbers probably mean nothing to you, and that's okay. But they're forming stars at rates of anywhere between 20 and 200 solar masses per year. So these guys are burgeoning. The Milky Way is forming stars at a few solar masses per year, and it's considered to be gas-rich. These guys are in what should be red and dead old galaxies, and they have more molecular gas than any of the spiral galaxies that may be sitting in these galaxy clusters. So we're quite certain, or pretty sure, that this stuff is just most likely it cooled out of the intercluster medium. So this is a result of the inefficiency of feedback to completely quench star formation. And our strategy was to go for CO1 to 0, which gave us a larger field of view and a little more sensitivity, and then go to CO3 to 2, which gives us a nice sharp image so we can see, where the gas is. And it's still a little qualitative because it's early days for this stuff, but we have a couple of interesting results. One of the big surprises to me was just the spectra. First of all, they're beautiful. I don't have time to show you what the old single dish spectra looked like, but they were really ratty compared to this. And with ALMA, the integrated spectrum, we get this beautiful signal to noise, but the thing that struck me when I first saw it was how narrow it is. Okay, if you have gas, it's it's either if it's in a disk, it's going to be supported by rotation. If the gas is coming in and it's not in a disk, it's going to quickly take on the dynamics of the stars at the center. And the stars at the centers of these galaxies have velocity dispersions of several hundred kilometers a second. And the full width half max of the gas in these things is somewhere between 100 and 200 kilometers a second. So the idea we had was that, for example, in this guy, which was the first one we saw this effect, we just got unlucky and we're seeing a disk that's nearly face on, and this is supported by rotation. And that might be true, but as I'll show you in a few minutes, I don't think it is. I think we've got something very interesting here. The other thing that we saw that was quite remarkable is evidence for outflow. And it's not a small outflow, it's a big outflow. And keep in mind, this is not a quasar. This is not driven by photons as you get in the early universe. This is just a radio source in the center of this. And what we found, in addition to this very narrow line at the center, we found a red wing on this side of the galaxy. So this is, in the visual, this would be a big giant galaxy, and what's shown here is the molecular gas. And we've never had resolution like this before. So this is sub-arc second resolution in the sub-millimeter, which is quite remarkable. But there's this central peak associated with the galaxy. There's this red wing here of gas that's red shifted, and then up in this direction here, there's blue shifted gas. And it looks a little innocuous in this picture, but when you integrate under it, there's more than 10 to the 10 solar masses of molecular gas associated with this. And the velocities are several hundred kilometers a second. There is too much gas going too fast to be driven out by radiation in this thing. There is plenty of energy in the mechanical jets. But the question is, how do you couple it to that? The other question is it an outflow or is it an inflow? This is seen in emission. Maybe the stuff is coming toward us. Maybe it's going away. We don't know for certain what that is, but I think which one it is. But I think the primary clue comes from looking at the center. If this were gas, first of all, there's 10 to the 10 solar masses of gas total in this system. So it's experienced infall in the past. There's 10 to the 10 associated with this flow. And when you look at the center, you see no high velocity gas. And if this stuff were coming in a steady flow, you'd expect to see high velocity gas at the center and lower velocity gas further out, and you don't. You see high velocity gas off nucleus and low velocity gas in the center. And so most likely this stuff is going out and it's not coming in. So the question is, what's throwing it out? And when we look in the X-ray, again, this is a fairly distant object, and this shows an X-ray picture of Abell 1835. And remember, in the visual, this thing is forming stars at the center at 200 solar masses per year. And you see these two X-ray bubbles right here. And it seems that the gas is roughly oriented in the direction of the bubbles. So it's possible that this stuff has just gotten dragged up with these bubbles as they rise out buoyantly. And this is a similar rendition. Now this is CO3 to 2, which shows us in great detail the gas. And primarily it's dominated by this thing at the center, which we think might be an edge-on disk, or a face-on disk, rather. I'm not convinced it is a disk anymore. But you see there is this hint that stuff is being dragged up around the edge of the bubbles.
What's defining zero velocity in your spectrum?
The redshift of the stars. And then finally, I mean, we've got several objects, but time is running out. I wanted to just show you our latest piece of data from ALMA. This one, again, is even weirder. This is Parks 0745, and this is a CO3 to 2 image that just showed up about a month and a half ago. And the X marks the center of the galaxy. And where you expect to see most of the molecular gas settled in a nice disk, which is where something that's hot, cold and dense ought to be, there's not much gas there. Most of the gas is off the nucleus of the galaxy. So this is the beam size of 0.3 arc seconds. So it's marvelously detailed. If we were to look at this in the visual, there'd be a giant galaxy sitting here forming stars at several tens of solar masses per year in the center. And all of the molecular gas, 10 to the 10 solar masses of it, so there's a lot of molecular gas in here. It's not even in the nucleus. It's not in a disk. And we've seen this in other systems where stars are forming, not necessarily in central disks, but in these filaments. Okay, it's not where stars are expected to form in galaxies. It's dusty. This is the weirdest thing has yet to come. It's dusty, which isn't surprising. You can see, I apologize for the quality of this, but I pulled this out of another publication. I haven't had a chance to overlay this yet, but you can see there are these dust filaments that nicely track this 10 to the 10 solar masses of CO. They lie just below the X-ray cavities. They're hard to see here, but there are these big bubbles sort of in this direction and this direction. And this is the cutout for this stuff, and it looks like these things are projected toward the bubbles. Is that proof, that these things were dragged out by the bubbles? No, not necessarily. But something happened to this galaxy, okay? It's forming stars. It's a fairly mature galaxy, and it's been forming stars for a long time. You'd expect this gas to be nicely settled in, feeding star formation, and it's not. So where did this come from, or what's happened to it? This is the other weird piece of the puzzle that we can't explain. The velocities are very low. Instead of the stuff flying out at hundreds of kilometers a second, or in the cases of quasars, thousands of kilometers a second, what we see on the left-hand side are the velocities. And the thing to keep in mind here is we've never been able to do this. This is just like brilliant data from ALMA, and it's only about 2 hours worth. Okay, so we can get this beautiful map both in velocity along the line of sight and velocity dispersion. And the thing to note is these numbers are small. We're not seeing large velocities. So if this stuff was dragged out, you'd expect it to be roughly at the buoyancy speed, which is about half the sound speed, or several hundred kilometers a second. So either it has nicely aligned itself so that most of the velocity is, in this direction and not in this direction. Okay, it's in the plane of the sky. Or the stuff, it's possible that this stuff is a cooling condensate that's just starting as the bubbles have risen over the last 5, 10 to the 7 years, but it doesn't explain the dearth of gas that's sitting down at the center of the galaxy. So we just, well, yeah.
You just take the X-ray emitting gas within a similar volume, just spherical.
Yep.
What's the ratio?
They're comparable.
They're comparable.
Yeah. Probably a little more X-ray emitting gas. I haven't done it for this one, but I've done it for 1835. And in the right in the center, well, over the entire region they're comparable. In the center where the gas is concentrated in 1835, the CO gas exceeds it dramatically. In this thing, I'm not sure, but I would say it's probably comparable given the size of it. But this has significantly less gas as well. So we don't know what's going on. First of all, if this stuff is being dragged out by the bubbles, how do you couple, gas that's 5 orders of magnitude denser to these light bubbles which are rising up by buoyancy? And how do you explain the mass of it? There's 10 to the 10 solar masses being dragged up. Bernoulli's law says you can't drag up more than you displace, and these bubbles have displaced probably 5 times that or 6 times that, but it's still very close to the mass of molecular gas. So something is dragging them out. It's not radiation pressure because there's not enough radiation to do it. There's plenty of energy in the bubbles, but it's not clear how you couple them. And in this case, I don't understand the velocities. Yet none of this gas is all being pulled out of the center. It's a mystery. I don't understand it.
The stuff
Yeah.
presumably would evaporate quickly unless heat conduction were suppressed, say by magnetic fields. Or...
Yeah. So the temperature of the gas, so it's a very steep temperature dependence on heat conduction, and the temperature of the gas is dropping dramatically in the center. So it's not clear how efficient heat conduction would be in the centers. It's probably efficient in the outer parts, but it's not clear that you can get this stuff to evaporate that quickly in these conditions. I think Ian knows more about this than I do, but I think that's a tough row to hoe. Okay.
Why couldn't you couple it with magnetic fields?
Well, that's another possibility. Norm has we've talked long and hard about this, and magnetic fields is I think you would agree. It's the obvious candidate. Yeah.
Can you imagine Siemens splitting in your lines?
I don't think at this. I mean, I haven't sat down and done the math, but I doubt it. And with this kind of resolution. Okay, we don't. For Zeeman splitting, I think you would need very high spectral resolution and high signal to noise, right? And the fields are weak. Yeah.
You book a circular because that doesn't blend. So when you Siemens splitting a small on your line widths, then the circular still survives.
I don't know, but I'd be surprised. We can sit down and work it out, but I haven't worked it out.
It's sub-millimeter or millimeter. Frequencies mostly you can do it in centimeter.
Yeah.
Because the velocity risks aren't so great in hertz. I mean, the Zeeman splitting measured in hertz, 3 megahertz per gas.
It's quite small.
So you're talking about a few hertz, and then the line width is V over C times the frequency. So you really need, you would like to have a long wavelength radio line, so the line isn't that much good and Doppler, and it also has to have a lambda G value, so you need to have electron lambda G value in ground state or whatever state. It's not easy to do. That's why we can't do it in molecular clouds, except for OH.
That was exactly what I was going to say, but I figured I didn't have enough time. So, but yeah, that's all I have. I'm already over time, and I've taken too much of your time, so I won't go through the conclusions, but I'll take questions. Thanks.
So in your grand picture, you put 1,000 solar masses a year of cooling mass, and the other things added up to maybe 100 that are coming out. What happens to the remaining 900 solar masses?
So no, the idea is that for the most part, it's just heated up. The cooling losses that comprise the 1,000 solar masses are 9/10 of that is just heated up. It's just replenished, and then
Cooling is neither a verb nor a noun in appearance.
I'm sorry.
The verb cooling is neither a noun nor a verb.
Okay. But what we can compare is luminosity to luminosity.
An illusion.
That's the argument.
Yeah. I'm sorry. Yes, it's an illusion. So there's energy going out. There's energy going in. 95% of the energy going out is replenished by the energy going in from the black hole. And then there's some residual, which there has to be an inefficiency or you won't have a feedback loop. And that's going into the cold gas and
But I will make an
stars.
comment to the theorists out there. Actually, how the heating works is completely not understood. It's just an energy argument. You infer by the inflation of those bubbles that there's that much energy going in, and somehow or other that magically can heats the gas.
Well, yeah, I mean, and people have worked on it. And so the idea is that you get about half of the enthalpy is back just from MGH. And you get this turbulent cascade, which then goes down to smaller and smaller scales. But there are people here who know more about that than I do. I mean, there are ideas out there, but you're right, we don't know.
Dick, you had a question?
Yeah, so I want to get back to the real beginning and view it from the point of view of a hopelessly naive modeler. I guess it's much harder to penetrate the early AGN regime than the radio regime because of scales and things. So
What do you mean by penetrate?
observe.
Oh.
So it's a question of how you get some sort of granification in the views of these two regimes. So this one is focused on the radio
Right.
regime, which is good, but from the point of view of simulation, you'd better get the early stuff right too, because that's really stopping the star formation early on. So I know that this is a huge topic, but are you able to go after any of that with the kind of new observational methods you've been up to, or is it all more localized?
No, so we're doing it in a slightly different way. We're going up in power, and there are a subset of systems that turn out are both quasars. They seem to be both in this mechanical and quasar mode. And the very interesting thing is if they're nuclear powers. So I said in this cartoonish way that we think what's dictating the power output, or the form of the power output, not necessarily the strength, but the form, is the structure of the disk. And we can explore that through the emergent properties by looking at the nuclear radiation coming from the center. And there is this subset of objects that are very bright in the center that look like quasars, but also have these big mechanical holes in them. And the theory would tell you that they shouldn't coexist because they should be in very different stages of evolution. But it may be that these are systems that are just on that threshold in Eddington units between being, these fast accretors and slow accretors. And so it may be that the accretion rates are varying enough where they jump back and forth between being a quasar and a radio source. And those, I think, are the key to understanding this transition and the relative importance of the two things. But you're right, that the standard view right now is that the M-sigma relation is imprinted very early on using the kind of outflows that Norm has worked on, and that at later times this is more or less a maintenance mode. But what I'm trying to motivate here is in these big systems, they're accreting at very high rates today. And in fact, just the radio mode itself for these big systems in the center will have doubled the mass of the black hole. So it's not an insignificant part of the growth of the black hole or the energy budget. And in fact, MS07, which is kind of the poster child for this thing, if you look at the M-sigma relation and the mass of the black hole it should have, it's possible on the low end of the M-sigma relation that that black hole doubled in mass in that single outburst. Most likely it grew by 10%. But it's a significant amount of black hole growth.
Ray had a question. So the iron in these iron streaks was presumably produced in supernova explosions. But is it just ambient gas that's being dragged out, which has the explosion is long in the past, or is it
It's in this case it's more or less ambient, because the remarkable thing about MS07, which deserves 10 minutes on its own, is there's almost no star formation in it. The star formation rate is less than half a solar mass per year, so it hasn't produced much. Oh yeah, well, 1As, if you integrate over about 2 billion years, it would produce the mass that's dragged out from type 1As. So it's consistent with just the ambient production of metals.
All right, so I think, okay.
If you have cold gas, which molecular gas has to be, and just maintaining it in the gravitational field so it doesn't fall down, you have to put a lot of mechanical energy in. And of course, that's going to bring in a lot of heat. You can probably make it's very hard to accelerate it.
That's why you need small aspect ratio,
It's
right?
very hard to accelerate without heating.
Yes, and keeping the velocity dispersion so low, yes. So there's a,
There's a lot of power coming out of steel lines.
yeah, that's right, yeah. So so there's an alternative.
My guess is that if you look at it, you'll find the acceleration that's needed. If you just assume that that's not going to be a nice laminar flow, that's where your heat comes from. And then ultimately that mechanical energy, since it's not some nice laminar flow, ends up as your heat.
Mm-hmm.
You can worry about exactly how it does, but there'll be some cascade down to small scale. Everything always ends up is heat. It's a sort of natural way for mechanical energy.
But you want to heat it to 10, as we were saying, 8 kV. Well, in the center, it's
Oh,
not that.
no. The molecular gas is going to be heated. It won't be molecular anymore. That's part of
Right,
it.
well, so why is it even there to begin with, yeah.
And once it gets heated more, it doesn't radiate as well. It most becomes lower density.
Right.
And then it's easier to heat it even more.
There's a competition here between, I mean, you need to have very small, obviously with this huge density contrast, right? You need to have a small aspect ratio to have some sort of hydrodynamical coupling.
You need a large area. You need a large surface area, okay, and
So then you fragment up the gas, which obviously you bring in the issue that it's coupled more efficiently to the hot gas thermally unless you suppress it. So it's also all consistent with it being some sort of dense network of
right, it's with a very low filling factor. So there's an alternative too. The average cooling time of this gas in the center is generally comparable to the rise time of the bubbles. So it's a few 10 to the 8th years. But there's a component of very cool, much cooler gas that's for the gas that's a few keV, say 5 keV. But there's also gas at many temperatures, and so the gas that's at about a half a keV, which again has a much larger volume filling factor and is much more easily lifted. In fact, we see it being lifted by the jets. Turns out that the cooling time in that gas is comparable to or less than the rise time for the bubbles. So one way out of this conundrum is to have the bubbles just suck out the gas that's cool, the warm gas, and have it cool in the wake of the rising bubble. And what we're seeing here is the CO that cooled in the rising wake of the bubble. And that way you get around the lifting problems and so on, and maybe we can solve the velocity problem, which is...
But it's fascinating, it's almost hydrostatic, it's basically.
That's what was really striking
Yeah.
about this one. I looked at those and thought,
Yeah.
that's a disc. Can't be anything. It's not true.
It's just has to be very tightly.
I mean, the first one might be a disc. It's a nice round source. It's incredibly narrow line. Maybe that means. But the rest of them all look, they're not discs. They
How
all
many
look-
examples?
Well, 5.
There are 3 or 4, yeah. No, that was a big moment for me because you were saying star formation only forms in disks, and it doesn't. And the thing is, this may be the dominant mode of star formation in the very early universe. Maybe in the very early, these galaxies, star formation didn't occur in two-ray unstable disks. They occurred in these filaments, which is what we're seeing here.
No, they weren't discs.
But how do you know there's star formation in that molecular gas?
We don't in that. And in fact, in 1835, it looks like the stuff that's dragged out is not forming stars. It's the stuff down in the center.
Central part
But
I thought was a disc.
this we need to get UV pictures of soon, I hope, to look to see. There is star formation, but I don't know if they're in those particular filaments.
There is also, in like Perseus, there's definitely a lot of H-alpha emission. There's a lot of dust in those filamentary structures.
Yeah,
There's these long tube-like things, and it's quite possible there's star formation going on.
there is actually in some of those, although the ones that we see star formation don't necessarily have CO detections, but it's there. It's just below the threshold.
We can continue this, I think, upstairs, so let's think about it.